thanking Katya and Newt for putting together this wonderful series of seminars. It's really been a great service to the inverse problems community to have a place where people can congregate and hear great talks and everything. So thank you. Okay, so I'd like to talk about some work from a year or two ago. Because of the pandemic, I really haven't had a chance to speak about this too much, which is on an application of microlocal analysis to radar, a very specific kind of radar called Doppler synthetic aperture radar. So this is joint work with Raluca Filea, Romina Gaburo, and Cliff Nolan. And I want to begin by just briefly discussing conventional or monostatic SAR, which I think a number of people in the audience know about, but I'll do it for the sake of completeness. And then I will discuss the version of SAR that we call Doppler SAR that I want to talk about. This actually is only one version of Doppler SAR. So I'll give the background on that. And then I will discuss the setup for the kind of imaging we want to do, discuss the main results. I will not give any proofs because most of the proofs really are just calculations, sort of a combination of multidimensional calculus and linear algebra, not super fascinating. So I'd rather discuss the content of the results, briefly talk about future directions. And before I go any further, I should acknowledge this is supported partly by the NSF, and also we were supported by a Square collaboration at the American Institute of Mathematics in San Jose. And we also would like to thank Margaret Cheney for suggesting this problem in the first place and for numerous discussions on it, especially in the early phases. Okay, so let's talk about conventional synthetic aperture radar, or SAR. So we have radar waves which are transmitted by aircraft or a satellite, so by an airborne or spaceborne antenna. And the waves scatter from features on the Earth's surface that we want to image. And in conventional or monostatic SAR, the reflected waves are measured by a receiver, which is co-located with the transmitter. So on the same aircraft, you have a transmitting antenna and a receiving antenna, or on a satellite. There are variations on this. So for example, in bistatic SAR, you can have the receiver, which is physically separated from the transmitter, or actually in multistatic SAR, you can actually have multiple receivers. And some of these may be mobile, some of these may be fixed. So there are various geometries one could consider. So I'm going to focus on monostatic SAR as something to compare what we're going to be talking about with at various points. So in monostatic SAR, the transmitted wave is comprised of a train of complex signals, which are cleverly designed to improve the temporal resolution and therefore the spatial resolution, and to improve the signal to noise ratio. After they're received by the receiver, they can be digitally signal processed, for example, by cross correlation with the transmitted signal and the received signal. And because these are complex signals, they're necessarily wide bandwidth. And what we'll be talking about is going to be a very narrow bandwidth version of SAR. Okay, so these kinds of transmitted signals allow, because they have very good temporal resolution after suitable processing, they allow for high resolution estimates of the two-way travel times from the transmitter back to the receiver after it's been scattered off of the Earth, and therefore gives high resolution estimates of the distances or ranges between the antenna and the surface. And you can use this information to construct surface features, for example, via filtered back projection techniques, making it much more similar to, for example, tomography and other situations where you can do filtered back projection. Okay, so there's a large literature on SAR. So I want to focus on that part of it, which is fairly mathematical in nature, which focuses on microlocal techniques. So again, because of the similarities with things like tomography or linearized seismic imaging, one can use certain approaches which basically allow you, at least in theory, to reconstruct singularities in the image from singularities in the data. And for some purposes, what we're really interested in is the singularities. Where does some physical parameter jump in value, for example? Okay, so we're going to focus on microlocal techniques. And there's a certain mathematical literature that involves analyzing the effect that the geometry of the flight path, typically for a flight path, we'd be talking about an airplane. And of course, for a satellite, it has a fixed flight path. But analyzing the effect of the flight path geometry on the ability to reconstruct good images. So characterizing artifacts or suggesting ways to either remove or avoid artifacts, for example, by beamforming, where you would only try to point the radar mainly in one direction. So there are many papers on this. So here are just a few that I'll mention. So there's some of the original papers in the mathematical literature by Cliff Nolan and Margaret Cheney in 2002, 2004, Raluca Falea, a paper of Falea, Gabor, Nolan, and also Stefanoff and Ullman, but there are many, many other papers. And also these microlocal techniques have also been applied to the bistatic situation and even multistatic situation, allowing for multiple reflections and various other variations on the original problem. Now in this setting, microlocal analysis is a reasonable tool to use for this kind of SAR because these complex waveforms that are used, that are transmitted, because they're necessarily wide bandwidth, they have a high frequency content. They have many frequencies in them, but in particular, they have some very high frequencies in order to allow for this complex structure, which means that microlocal analysis, which is high frequency asymptotics, is a reasonable tool to apply. And it's been quite successful. So again, these microlocal techniques have been used in tomography, linearized seismic imaging, various kinds of conventional SAR. And so now we'd like to also take this point of view for a different kind of SAR called Doppler SAR, which uses Doppler radar. So it uses relative velocity data rather than range or distance data. And since, sort of by definition, Doppler SAR is narrow band, which you need to do in order to detect the Doppler shifts, because it's narrow band, it's actually not obvious that microlocal analysis should be useful, because again, microlocal analysis is a high frequency asymptotic technique. If you're talking about narrow band, that means it's essentially working at one or very close to one fixed frequency. But we know from experience that in fact, high frequency asymptotics can be useful even if the frequencies aren't terribly high. And in fact, in this case, we have positive results to show that in fact, this is, we think, a useful approach. The overall picture here is there is a model which has some rather large gaps in it in terms of things that are not mathematically justified, right? So we make various approximations, which I will describe in the next few minutes. Eventually we get to a point where we can start using solidly grounded microlocal analysis, and that's what I will focus on. But there are a number of approximations along the way, any one of which one can argue with, and we do not have rigorous results, sort of proving that this approximation is actually a good approximation. But that's just the way it is. Okay, so let me give an overview of Doppler SAR and then go into it in a little bit more detail. So the goal is to image a stationary scene on the Earth, and we'll imagine the Earth as being flat, using Doppler SAR data collected from a flight path or a satellite trajectory, which is at a constant altitude, just to make life simpler. All of these things, of course, could be modified. So we'll eventually focus on two model flight paths, a linear flight path and a circular flight path, and we'll analyze the artifacts and describe artifact-free regions or ways to avoid artifacts using beamforming and so on. Now, doing this just for two particular flight paths, a straight line and a circle, may seem rather specialized, but there are a couple issues here. One is that the calculations, more for the circle than for the linear case, the calculations actually are quite complicated. And so actually we don't know, for example, how to extend the calculation from a circle to a general path with non-zero curvature. Almost certainly our result is still the same, but we don't actually know how to do that calculation. So the calculations involving the microlocal geometry, the canonical relations, are just messy, and therefore there's a limit to what we can do at the moment. And also there's certain other features that come out from these two model cases that we'll see as we go along that we think are more applicable. Now, the analysis involves, as I said, multiple approximations, each one of which one can certainly ask, is it justified? The most important of these are the following. First of all, we use a single scattering or Born approximation. Of course, this is very widely used. It certainly would be interesting to try to see what happens in the presence of significant multiple scattering for some kinds of features on the Earth's surface that might be of interest. We have not done that. Secondly, we assume a specific form of the reflectivity function, which I'll define in a few minutes. One can certainly argue with this particular choice. It's designed to concentrate all the activities, so to speak, right on the surface of the Earth, but the particular form we choose, which is used elsewhere in the SAR literature, one certainly can argue with that. And then we make an approximation which is fairly widely used in radar called a start-stop approximation. And furthermore, there's a linear approximation on top of that. And again, one can ask whether this is justified. And we, at the very end, I will describe some initial attempt to relax, or rather refine, the start-stop approximation. And one of our results is robust to an improvement of the this approximation. We still get the same ultimate result, which is reassuring. So modifying these, any of these to make the model more accurate would certainly be interesting. It could potentially change the conclusions, but it is what it is, as they say. Oops, now for some reason. Okay, so let's get a little bit of history about Doppler and SAR. So first of all, of course, Doppler radar used in frequency shifts is very familiar. So collecting from a stationary receiver, collecting data about moving objects. One sees this all the time in weather radar. It's also been used in planetary astronomy, measuring either velocities or rotations of planetary objects or asteroids. So Doppler radar is certainly well established. You can also try to combine Doppler and SAR to image fixed objects from a moving platform. So this was proposed by Borden and Cheney in 2005. And it was studied further in a variety of ways. So for bistatic data, it was studied and actually was called Doppler SAR by Wang and Yassizi in a couple of papers. And then there are also a number of quite related approaches in the engineering literature. And I should say that outside of the mathematics literature, obviously there's a huge engineering literature, which I will freely admit I'm not totally conversant with. So here we want to study one particular way of combining Doppler and SAR, which we'll call monostatic Doppler SAR. And we'll do that for some model flight paths, as I said, a straight flight path and a circular flight path. And what we'll see is that after a suitable mathematical manipulation of the raw data, basically a filtered, windowed Fourier transform, the resulting forward scattering operator becomes a Fourier integral operator, and therefore techniques of microlocal analysis become an appropriate tool to apply. So let's now describe this in a little bit more detail. So we have the following picture. We have an antenna moving along, again, either an airplane at some altitude or a satellite in near Earth orbit. So this antenna moving along a flight path gamma of t, and we'll pretend that it's at constant altitude h. And again, we're going to pretend that the Earth's surface is flat at altitude 0. And along with the transmitter, there's a co-located receiver, which will measure the waves which are scattered off of the Earth and come back to the receiver. So in order to obtain high resolution Doppler shift measurements, since a Doppler shift is a shift in frequency, we want to transmit a very narrow band or even single frequency signal. So this is a continuous wave or CW signal at a single frequency, say omega naught. Right? So that's all the transmitter is doing, is it's emitting this continuous wave signal. So in our model, we're going to make this as simple as possible. We're going to ignore polarization. And so we're going to model the electromagnetic wave using just the scalar wave equation. So we let E of t be the electric field, or rather one component of the electric field. Here we have the wave equation. We're going to use coordinates boldface y in R3, where y3 is the vertical component, and the sound speed, so the light speed is c of y, the wave propagation speed. And we're going to assume that c of y is actually constant until you get right on the surface of the Earth. So I'll say more about that in a second. And this is an inhomogeneous wave equation where the right-hand side describes the source, namely our transmitter, which is sending out this CW signal. So we have this wave equation we want to solve. So we model the continuous wave source simply as FTY is, we have the oscillator e to the negative I omega naught t. And then you have the fact that that is a delta function source at the point that you're at the point that the transmitter is at time t, which is at y equals gamma of t. Now we're going to assume here that the transmitting antenna transmits isotropically. So at the beginning, there's no beam forming. For beam forming, it would be anisotropic. That would affect the amplitudes in the calculations that we do, but it would not affect the phase function in the FIO or the resulting geometry. And therefore, for the most part, we will suppress the amplitudes. We will mention the order of these symbols, of the amplitudes, but the exact form we're not going to worry about. Of course, for a real world application, you would be worried about them. In particular, you would care about them for beam forming. So we're going to make several assumptions. Assumption number one is, as I said, we'll assume that between the flight path and the ground, until you get right down to the features that you want to image, we'll assume that the speed of propagation is simply the speed of light in dry air. So just a tiny bit less than it is in a vacuum. So we're going to make that assumption. I guess in situations with very high humidity, then in fact, C of y can be noticeably less, but we're just going to assume this for simplicity. So that means above the Earth's surface, we just have the free wave equation. Right? And then we look at the so-called reflectivity function, which is the difference between 1 over C0 squared and 1 over C of y squared. And so it's a difference in the coefficients in the wave equation for the free equation and the inhomogeneous equation, the heterogeneous equation. So now we make a second assumption. And so this is a rather strong structural assumption on the reflectivity function. So we're interested in imaging things on the Earth's surface. The signals coming from either airborne or spaceborne transmitters attenuate very quickly in the Earth once you get into the subsurface. So it's reasonable to assume that the reflectivity assumption, the reflectivity function, is supported very close to the Earth's surface, or maybe even right on the Earth's surface. But the specific form we assume is the following. We assume it's of the form a function of y1 and y2, so a function on the Earth's surface, v of y prime, times the delta function of y3. So of course, the delta function is supported at y3 equals 0, but there are other distributions that are supported at y3 equals 0. So one can, certainly argue with this assumption, but this is the assumption that we're making. And it's also made in a number of the other papers in the mathematical SAR literature. So we will refer to this unknown function of two variables, v of y1, y2, we will refer to it as the scene. And it is this function of two variables that describes the features on the Earth's surface. It's this function v that we want to reconstruct from the DSAR data. Okay, so we do a formal linearization. We think of C as C0 plus delta of C, right? Even though, of course, delta C is quite singular. Right? And then that results in an electric field, which is E0, which would be the incident field in free space plus delta E. And the perturbation, delta E, satisfies this wave equation here. So we have the free space wave equation, wave operator on the left. That operator applied to delta E is equal to the product negative V of Y times del squared E0 T of Y. And that actually should be times the delta function of Y3. I left that out. I apologize. Okay, so this brings us to the third assumption, which is a start-stop approximation. So we assume here that the speed of wave propagation, which is essentially the speed of light, is so much greater than the speed at which your transmitter and receiver are traveling that for this approximation, the point at which the scattered wave is detected, is the point at which the scattered wave comes back to the platform and is measured by the receiver, is the same as where the antenna originally transmitted it. In other words, the wave goes down and comes back so quickly that the platform has hardly moved. So certainly for an aircraft, a subsonic aircraft in the atmosphere, and given the distances involved, this is an extremely reasonable assumption. For a satellite in near Earth orbit, given the distances and given the speed, maybe it's a little bit less of a reasonable approximation. But nevertheless, for most of the talk, we will use this approximation. We will tweak it a bit at the end and see that one of our results is robust to the improvement. But in any case, this is the start-stop approximation. So as I said, it's widely used in radar, including conventional SAR. For the kinds of transmitted waves we're using, these continuous waves, e to the negative I omega 0 times t, it's harder to justify because the wave is going continuously, right? But in fact, we can sort of justify this after the fact, because as we'll see at the end, for a linear flight path, further correction to the start-stop approximation, basically a first-order correction, actually leads to the same ultimate conclusion as when you make the start-stop approximation. Even though, in fact, the geometry involved is somewhat unstable, nevertheless, when you improve the start-stop approximation, at least somewhat, you get the same final result. So that is some supporting evidence that, in fact, it's a reasonable thing to do to use the start-stop approximation. Furthermore, for the circular flight path case, then the FIO geometry turns out to be structurally stable, which means that at least under small perturbations, it would still have the same overall geometry. Of course, going from the start-stop approximation to an exact modeling of the return time might not be a small perturbation. So that's not proof of anything. Again, at least it's reassurance. Our results are either stable or not. Further improvement on the approximation still gives the same result. Okay, so let's write down some formulas. So we're going to denote a point on the surface of the Earth by boldface x. So that has coordinates x1, x2. That's filling in for what I was calling y prime before. So let boldface r of t be the vector from the point gamma of t on the flight path down to the point x0 on the surface. And let just regular r of t be the length of that. That's the range or the distance from gamma of t to x. Now, of course, r of t, both of the r of t's depend on x in an important way, but for obvious notational reasons, we will suppress the dependence on x in most of the formulas. So under the start-stop approximation, the total time of travel for a transmitted wave, so going from the transmitter down to the surface, so you started at the point gamma of t, you go down to the surface to the point x0, and then you reflect back. The total travel time is the total distance traveled, which under the start-stop approximation is 2 times r of t divided by c0. Since that's the speed of propagation everywhere between the transmitter and the surface. We then solve the PDE on the previous slide using the Green's function for the free wave equation. And that means that the scattered wave measured on the antenna is a function just of the variable t. It's, in other words, delta E measured on the flight path. It's given by this integral here. So it's v of x integrated over R2 against a weight, a p of tx, which is antenna dependent. So for example, if you were beamforming, that would appear there, right? We will basically ignore that. And then the important thing is the oscillatory term in front. And then the spread factor on the bottom there, the 1 over 4 pi r of t squared, that is for our purposes, is really a smoothly varying function. It doesn't have oscillation in it. And so that too will be absorbed into the ultimate amplitude of our FIO. Okay, now d of t is a function of one variable, right? So we are going to turn it into a pretend function of two variables by doing a windowed Fourier transform. Right? Since we're starting with a function v of x1, x2, right? In order to recover that, we need a function of two variables. And so we will create a function of two variables out of d of t by this windowed Fourier transform. So in order to justify this in quotes, because in fact, again, this is not rigorously supportable from the point of view of pure mathematics, we can make the following comments. So as in many radar problems, there are multiple time scales because of the different speeds of various things and various distance scales. So for example, with the speed of light being roughly 3 × 10⁸ meters per second, as I said before, that's much, much bigger than the speed of the plane or even of a satellite. It's also true that the frequencies involved are very large. So typically you'd be doing this in a gigahertz or multi-gigahertz band. So omega 0 is at least 10 to the 9th. And so we sort of put these things together in the following way. We are going to analyze the received signal d of t by introducing two variables, namely a slow time s and a frequency omega. So s is basically replicating the fact that you're moving along the trajectory, which is relatively slow compared to the speed of light, right? And also a frequency omega. So how do we do that? So we are going to multiply d of t by a windowing function, right? So for each value of s, we're going to look at t's that are quite close to s. And the duration of this windowing function is going to be small relative to the antenna motion. So in other words, of the distance of the antenna, and again, the two antennas are co-located, so the transmitter and the receiver, the distance that they travel during the window of this windowing function is small relative to the wavelength of the wave. But on the other hand, the window has a duration which is large enough so that the transmitted signal undergoes enough oscillations, enough cycles over the support of the window so that it's reasonable to try to do Fourier analysis. So we introduce a windowing function that we'll call little l. So L of t is a smooth function. Say it's identically equal to 1 where t is less than or equal to capital L, and it's supported outside of the interval from negative 2L to 2L, where capital L is an appropriately chosen parameter involving all these physical constants that are in the problem. And so what we're going to do is we're going to take the window function to be of the form L evaluated at omega naught times t minus s. So for each value of s, we look at t's that are quite close to s, right? And we put in this scaling factor omega 0, which is the frequency of the continuous wave, which is being transmitted. Okay, so now although this windowing function is in fact a smooth function of compact support, we should actually think of it as a symbol of order 0 from the point of view of doing microlocal analysis. And the reason for that is if you look at how these functions behave as you vary the frequency omega naught, And as you vary the parameter L, which depends on various physical parameters in the problem, the entire family of functions, L of omega naught times t, that family will be a bounded family in the space of symbols of order 0. So this is just like when you do a Littlewood-Paley decomposition, or you localize in microlocal analysis, you localize to a frequency shell of size 2 to the k for some large value of k. Those cutoff functions, those Littlewood-Paley cutoff functions, the way to think of them is it's really a family of functions which are a bounded family in the space of symbols of order 0. Each one, by being of compact support in the frequency variable, is actually a symbol of order -infinity, but the entire family is behaving like uniformly like a family of symbols of order 0, and that's the way we will treat it in the analysis. Okay, so using the expression 3 for dt from a couple of slides ago, and then applying this windowed Fourier transform like this, we produce a function that I'll call w sub 0, because we still have another thing to do, w sub 0 of s of omega, and it's given by this expression here. Okay, so there's one more thing we need to do, which is we need to take the r of t that's in the phase, and we need to expand that. We need to Taylor expand that about t equals s. Now there's also an r of t in the denominator, but as I said before, that's not so important. That's a nice smoothly varying function and therefore can be put into the amplitude. So we Taylor expand that r of t that's in the phase about t equals s, and we just use the first two terms, the linear terms, and we'll always use a superscript dot like that to denote differentiation with respect to time. So we keep only the linear terms of the Taylor expansion. And then we do a change of variables where we place t by a parameter, by a coordinate, a variable we'll call tau, and tau is equal to t minus s. And we do that, we get the following. So this is going to be the thing we want to study. We'll call it w of s omega. And so that turns out to be the following integral. The outer integral is an integral against v of x dx. So the thing inside these square brackets is going to be an integral kernel. And that is in fact a Fourier integral distribution. In fact, it's the conormal distribution. Namely, we have a phase function here. That phase function has one phase variable tau. So there's a one-dimensional oscillatory integral in the sense of Hormander with the phase variable tau. So here's the oscillatory piece with the phase function. And the part on the second line that's grouped together that I call it A, that is a product of a bunch of things. And sitting in the front of it is this L of omega 0 times tau. And as I said, the way we should think of that, even though it's compactly supported in tau, we should think of that as actually a symbol of order 0. And then it's multiplied by this exponential here, which is harmless because it's independent of tau. So it's just a smooth function in terms of the variables s omega and x. And then we have the spread function. So this is a Fourier integral operator. We have a phase function, we have a nice amplitude, and we want to study it. So this leads us to the DSAR transform. So this is the map which takes the seen v of x, the thing we're trying to image on the Earth's surface, to this windowed Fourier transform of the data, which is w of s omega. And it has a phase function phi, which is a function of the spatial and temporal variables s, omega, and x, and then the one phase variable tau, and it's simply tau times this smooth function of the other variables. And notice, of course, as I said, R really has an X dependence that we have suppressed to keep the formula smaller. So this phase function here certainly does depend on X as well as S and omega. And here R dot is the time rate of change of the range function. Okay, so this phase function is actually a linear function of tau. It's a tau times a function of the other variables. And this is a non-degenerate operator phase function in the sense of Hormander. As I said, the amplitude should be considered as an amplitude of order 0 and tau. And therefore, we have the following result, that under all the assumptions we made above, the mapping F is a Fourier integral operator of order -1/2 if you follow through Hormonder's numerology. And it's associated with a canonical relation, script C. So this is contained in the cotangent space T star of R2 for the S omega variables cross T star of R2 for the variable on the surface of the Earth, X, which means X1, X2. It's given by this expression here, and you have coordinates on the canonical relation, which are S ranging over the real numbers, X running over R2, and tau running over the non-zero frequency variables. Okay, now it's well known from applications of microlocal analysis to integral geometry, to linear and linearized inverse problems, that in order to understand what's going on, one should study the projections from this canonical relation down to the left and to the right. So we have the projection to the left, pi sub L, which sends a point on the canonical relation to S omega and the dual variables for those two variables, which are sigma dual to S and tau dual to omega. And the projection to the right, which goes down to the cotangent space of R2 for the spatial variable. So that's X, comma C. So you want to study the structure of these projections. So it's known from general facts about canonical relations, at any point lambda 0 in C, if the determinant of one of these projections, say pi r, if you look at the differential of pi r, so pi r is going from a 4-dimensional space to a 4-dimensional space, d pi r is essentially a 4x4 matrix. If the determinant of that is not equal to 0 for the projection on the right, then the same thing is true for the projection on the left and vice versa. And then in that case, near this point lambda 0, C is a local canonical graph. Now, if we strengthen that by adding the condition that pi L is globally 1-to-1, that in tomography that's called the Bulker condition, introduced by Gilliman, in linearized seismology that's called the travel time injectivity condition, introduced by Nolan and Symes and others. If this is true, this gives us that F star F is a psi DO of order -1 as an operator in the X variable. So once you have that by well-known techniques, you can then write down good inversion formulas or approximate inversion formulas to image the scene V from the data, from the process data. In particular, since we can invert modulo C infinity, we can determine singularities in the scene, singularities in the sense of discontinuities or other kinds of non-smoothness. We can determine the singularities of the scene from singularities in the filtered windowed Fourier transform. So that's the ideal situation if the Bulker condition or the analog of that is satisfied. So what we need to do is, for the flight paths that we want to analyze, we want to determine whether or not this is the case. We want to look at the points, if any, where the determinant of the differentials of the projections are equal to 0, call that sigma, and find sigma inside of the canonical relation. And if it's non-empty, that's bad news. We want to study the structure of pi r and pi l at sigma. And furthermore, because of this one-to-oneness condition that's part of the Bulker condition, we also want to study the projections globally. So let me describe our main results. So first of all, for a linear flight path, we have the following. So if the flight path gamma is a straight horizontal line, then the canonical relation C, to which this operator, which takes the scene V of X to the windowed Fourier transform data W of S omega, the canonical relation is what's called a fold blowdown, meaning that where C is not a local canonical graph, in fact, pi L has a Whitney fold singularity, while pi R is a blowdown. Okay, so in other words, it's not covered by the Bulker condition. It's degenerate in some way. So this results in there being a left-right artifact about the projection of the trajectory down into the Earth. So little gamma is our flight path. If you project little gamma down into the Earth, we call it capital gamma. It's just a straight line. And it's well known in radar situations involving straight lines that you often get a left-right ambiguity, and that happens here as well. So there's a left-right artifact about the projection capital gamma down on the Earth. If we beamform to the left or to the right, which basically is controlling the amplitude, then the artifact can be eliminated, in which case the process data W determines any scene down on the Earth modulo C infinity. So if the scene V is just to the right of the flight path or just to the left of the flight path, we can reconstruct it modulo C infinity. Now it turns out this is exactly the same thing that happens for conventional monostatic SAR with a linear flight path. So in some sense, there's no difference in terms of the artifacts and how you would deal with them between standard monostatic SAR and Doppler SAR for a straight flight path. However, that's not the case in the case of the circular flight path. But before I say that, let me say a couple more things. So in this case, you can identify the Schwartz kernel of F star F, the so-called normal operator. In fact, it's known to be a paired Lagrangian distribution. So its wavefront relation is not only part of the diagonal, which is what you would have if F star F were a psi-DO, which is what happens under the Bolker condition. But in addition to the diagonal, you get another canonical relation, which in fact is another canonical graph. And that results in a strong artifact unless one beamforms. So this was shown by Verlucke and Fillet in 2007. So in fact, what happens is that the wavefront relation of F star F is contained in the union of the diagonal and the graph of a canonical transformation, the graph of a canonical involution. And this is simply the canonical transformation, which is induced by the reflection about the flight path. X1, X2 goes to X1 minus X2 if our flight path were right above the X1 axis. And it's well known that the graph of chi intersects the diagonal cleanly in codimension 2. And in fact, Verlucke showed that the Schwartz kernel of F star F belongs to one of these paired Lagrangian spaces, these IPL spaces introduced many years ago by Melrose and Ullman and Gilliman. And it has the same order. F star F has the same order, namely -1, on both the diagonal piece and the graph of chi, which means the graph of chi piece is a strong non-removable artifact. And so the only way to deal with it essentially is by beamforming or to live with the left-right ambiguity if you're willing to live with that. So that's what happens for the linear flight path. Exactly the same thing happens for monostatic SAR. So what's different now is for a circular flight path, then in fact the canonical relation has a fold cusp singularity or degeneracy, meaning that the projection to the left is still a Whitney fold, just as it was before for the straight flight path. But now pi r, the projection down into T star of the Earth, has singularities up to and including simple cusp type. So in C infinity singularity theory, there is this stratification of at least one particular class of singularities. The best ones are the Whitney folds, then the cusps, and the swallowtails. So in this case, we now are dealing with some points where you have a simple cusp type singularity, which is worse than a Whitney fold. For a scene V with suitable explicitly describable support and by suitable beamforming, in fact, you can avoid any artifact. So we give a fairly explicit description, which I'll mention in a moment, of a region which is guaranteed to be artifact free. And then the windowed Fourier transform determines the scene up to a possible C infinity error. So this is actually more degenerate. This is actually worse than what happens in monostatic SAR for a circular flight path. So that was studied by Nolan and Cheney in 2004 and again by Verlucke in 2007. So this is a little bit of a surprise that same trajectory, obviously a different kind of SAR, but the FIO geometry is worse. Now, it turns out that this same fold cusp kind of geometry comes up in another place, which is again monostatic SAR, but when gamma is not circular, but it has a simple inflection point. So you imagine your airplane wandering around and maybe turning from left to right. So there would be simple inflection points. And at those points, it was analyzed by Fourier and Nolan. And they show that, in fact, what happens is that, again, you have a strong non-removable artifact. That's not too surprising that it's at least as bad as in the circular case. But the non-diagonal part of the wavefront relation is, in fact, an interesting kind of object. It's a object called an open umbrella, which is something that's been studied in symplectic geometry. An open umbrella is basically the simplest kind of non-removable singularity that a Lagrangian manifold can have. And this has come up before. It also came up in a seismology problem that Reluk and I studied involving caustics of cusp type. But it also comes up in monostatic SAR for gamma with an inflection point. Anyway, that same geometry comes up here. So it's known that the artifact is strong, and it's even worse than before because it's not even a smooth set, not everywhere. Okay. However, to be on the positive side, we can give a concrete region where, in fact, you can avoid artifacts. So let's describe the circular flight path in the following way. Let's describe gamma of t as rho cosine t, rho sine t, rho h. So the radius is rho, center of the origin, and the height is rho times h. So h here is a dimensionless parameter. And what we show is that if you look at the surface region, which is the disk centered at the origin of radius rho times this dimensionless number 1 plus h squared over 2, then the canonical relation is artifact free. The operator is artifact free over that region. And therefore, if you beamform to that region, then in fact, you'll get good imaging. It's as if the Boltzmann condition is satisfied. Now, an interesting point which we have not pursued, which would be perhaps interesting to pursue, is that it turns out that if you compare the artifact region down on the artifact points down on the ground for the circular flight path for monostatic SAR versus Doppler SAR, in fact, the artifact sets are disjoint. So this raises the possibility of perhaps combining conventional SAR data with Doppler SAR data and then doing some processing to obtain artifact-free imaging. And so you wouldn't have to worry about either the fold points from the monostatic SAR or the cusp points from the Doppler SAR. You would get a good image, but we have not pursued this. I just have a couple more minutes, so let me quickly say the following. So going back to the linear flight path, we have a correction, a partial correction to the start-stop approximation. And the result that we obtained is robust to this additional improvement on the start-stop approximation. And the reason that this is of interest is because the geometry for the canonical relation in the case of the straight flight path is a fold on the left and a blowdown on the right. And as I said, a fold is structurally stable. Under small perturbations, it's still a fold. But blowdowns are highly unstable. Almost any perturbation to a blowdown is not a blowdown. But we show that under this first order correction to the start-stop approximation, in fact, you still get a fold blowdown, making us somewhat reassured. Okay, so I'll run through this fairly quickly. So recall that the range R of t was given by this formula here. And t sub tot was the total travel time for the wave from transmitter to scatter back to receiver. And t tot is determined implicitly by this equation here. Right? And the start-stop approximation, pretending that in fact really the platform is not moved at all by the time the scattered wave comes back, that leads to the assumption that RT plus T tot is the same as R of T, and that leads to T tot being 2 R of T divided by the speed of light. So we refine this by expanding this thing on the right-hand side here, by expanding this about T, and this approximation to this formula becomes this, and solving for t tot and ignoring the terms that are a big O of C0 to the -3, we obtain this improvement on the approximation to t tot. So we have the same main term as before, and then we have this correction. And under that refined approximation, the scattered wave arrives at this time here. So we plug this refinement into the windowed Fourier transform. And then we have to do a substitution into the phase function. And in the phase function, we actually have to not only do a Taylor expansion of R of t, we have to do a Taylor expansion of R dot of t about t equals s. And so that involves the second derivative, R double dot of s. So anyway, you put it all together, you calculate modulo t minus s squared, and finally you come up with a similar expression. We'll call this W sub 1. So this has this first order correction. Again, it's an FIO. It has a phase function, it has an amplitude of order 0. And the phase function now is this. So the phase function up to the R dot over C0, that's the same phase function as before, but now there is this additional correction term, which is big O of C0 to the -2, so it's small, but it's a correction term. And when you do the analysis, which I'm not going to do, it turns out that the modified canonical relation is still a fold or blowdown type, which we were happy about. Okay, so as I said, folds are structurally stable, so it's not that surprising that under this refined approximation, pi L is still a Whitney fold. However, that is not at all guaranteed for pi R, and yet that's still a blowdown, and the analysis we gave is still valid. Okay, so let me just conclude with some open questions. So for a linear flight path, can we completely remove the start-stop approximation? In other words, working with the exact function t tot, which is really implicitly defined and therefore awkward to work with, can we actually show that still you get a blowdown fold structure? Now for the circular flight path, we didn't even do the first order correction because it turns out that the calculations got messy very, very quickly. That still remains to be done. And then you would have the first question as well. Can you simply do away totally with the start-stop approximation? Can we get the structure of a fold cusp that we got for the circle? Can we do that for a general flight path with non-zero curvature and with a reasonable description of an artifact-free zone? It seems like you should be able to, but again, the calculations are very unpleasant. And then finally, can we make the model more physically realistic? There have been a whole slew of approximations that we made. What are the effects of multiple scattering? Can you say what happens when your transmitted wave is not exactly a frequency omega 0, but is very narrow band? And there are many other such questions. So with that, I will stop and say thank you.
Thank you very much, Allan. Thank you very much for the nice talks. Are there any questions or comments?
Let's see. Hi. Yeah, that was a very nice talk. Thank you. I was just going to say, I think the thing about the start-stop approximation, I think it's maybe just an issue of nomenclature or something. I mean, in this context, it's kind of confusing because if you imagine your radar stopped, then there wouldn't be any Doppler shift. But I think it's really more, at least in the engineering literature, the way it's usually analyzed is how far does your antenna move during the time that it's transmitting and receiving, and how is that distance related to the size of your resolution cell? And for most radar systems, it's really, you know, the pulses are so short that it doesn't really move very much. So I think it's really fine. But anyway, the analysis is very nice.
Okay, but isn't it true that it's with the CW wave, with the continuous wave, I mean, there's no way to say when, there's no pulse to stop, right?
Yeah, but then you have the window, right? So you have, yeah. So.
Thank you very much. Are there any other questions or comments?
This is a very primitive one, but right from the very beginning, when you define the scene, since you have a flat Earth, level flight, what does the scene represent?
So it's some object, a scattering object right on the surface of the Earth. So you can imagine a low building, a tank, some engineering infrastructure. I mean, highways, canals.
But it's not. Is it given as a perturbation of the distance? Because it appeared to be in a sound speed in the way.
It was built into the reflectivity function. So again, as I tried to emphasize, the idea is you want the reflectivity function to be concentrated on or near the surface of the Earth. Doing it with a delta function is, of course, a very extreme thing to do, right? You would think that it might have, as a function of the vertical variable x3 or y3, it might have a very, very sharp profile. But having a delta function there is, of course, a mathematical idealization.
Okay, thank you.
Yeah, I mean, I fully share your discomfort because, I mean, it seems like a somewhat arbitrary choice, but it does concentrate things right on the surface, which is what we're trying to do, right? Why it's not a derivative of the delta function, or why it isn't, in fact, not completely supported on the Earth, but slightly, if there's a narrow layer, that would be worth looking at.
Okay.
Thank you very much. Are there any other questions or comments? Okay, any other questions or comments? Please unmute yourself.
Maybe a follow-up question about the previous question. What's the physical meaning of this sin function? What's its reflect?
So in other words, we're trying to have some kind of a cartoon version of something that sits right on the Earth's surface. So in other words, you have a perturbation in the propagation. So the propagation speed is supposed to be constant, right? Not even smoothly varying, constant down to the Earth's surface. And then you want something which will produce sharp scattering events, right? So in some sense, you're trying to replicate a scattering object, right? Like an obstacle. You're trying to replicate that by means of what's essentially a potential.
So it's more material property of the scatters, or it's the surface orientation of the scatters?
Both. So in other words, because we're using microlocal techniques, we're only working modulo C infinity. So we're recovering, when it works, we're recovering V of x1, x2 modulo C infinity from the process data modulo C infinity. So in other words, that you're picking up the singularities, which means, if you think about it, for example, in terms of wavefront set, that involves the orientation of interfaces. So if you have walls, right, you would pick up the locations and orientations of, features of the surface, but it's even, it's slightly better than that because you're picking up, I guess, what you would call a micro function. You're picking up a distribution modulo C infinity. So you're picking up both material parameters when they have jumps or just other kinds of non-smoothnesses. So you're picking up both locations and orientations, but also sizes of jumps.
And so you can think of it as how much energy comes back to the radar from that location on the Earth. And that can consist of, number of effects on the material, but also the shape, just as Allan said.
Yes.
I've got to run. So thanks, Allan. Take care.
Thank you very much. Thank you. Are there any other questions or comments? Any other questions or comments, please? Okay, if not, thank you very much, Allan, for the great talk. Thank you very much. Thank you very much, everyone, for coming. Thank you.
Thank you for the series.